So, today we are going to start the subject that we will be working on for, the next 10 days probably. So, okay? The reason we spend so much time on it is because it's one of those fundamental skills that we have to have, okay, in order to be able to do things not only in this unit, as well as in Unit 2, okay? It comes into play a lot over the next 2 months. Right? So it's definitely something we need to practice. Okay? It does tend to be one of the more difficult concepts, okay, for people, and that's simply because they have to get their head around the trigonometry. Right? Once you get your head around the trigonometry, these types of problems are very, very formulaic. Okay? And what I mean by that is it's like following a recipe in a cookbook. As long as you learn the steps, all you have to do is continue to follow the steps, and you basically can't go wrong on any of them. All right? Everybody with me so far? Okay. So some of the stuff we're going to talk about, you will have done before in Science 10. It won't look quite the same because we simplify it quite a bit, okay? But it is essentially still the same stuff that you did in Science 10. When you were adding, let's say, in a question where an object went north and then turned around and went south, okay? Those are simple, what we call colinear vectors because they're one-dimensional. They're north or south, left or right, up or down, okay? There's only a positive and a negative value. By the end of class today, we'll probably have moved on to perpendicular vectors. This will be new, right? In Science 10, you didn't have any questions where an object went north and then turned and went east, right? Because now that's a two-dimensional vector question, okay? We're going to have an angle in there. We're going to have a compass direction other than due north or due west, okay? It'll be X many degrees east of north or whatever. Okay, and that's going to involve, again, some simple SOHCAHTOA type of calculations. Next week, we'll get into the really involved ones where you're going to be adding vectors that are neither collinear nor perpendicular. Okay, they're all angled at different angles, okay, and you've got to figure out what the end result of that would be. Right? So the purpose of vector addition is to be able to add any two vector quantities and get their what we call vector sum. So let's say I had a trip, okay, where a person went 20 degrees east of north for, let's say, 100 meters, right? And then after that, they went, let's say, 35 meters, but they went, let's say, southeast. So they went like this. They went okay, so let's say they did those two things. They went 100 meters at 20 degrees east of north, and then they went 30 meters at 10 degrees south of east. Okay, this is what they did. What was their distance traveled? 130 meters. Remember, distance doesn't care which direction we go, just how far we went to get there. Calculating this object's displacement, I have to calculate their change in position, right? This is their starting position. This is their final position, right? And we know that displacement is final position minus initial position. The only problem is I can't do that. This isn't a graph. Okay? I actually have to figure out how long that line is and what direction it's going. Okay? Because that line will represent my displacement. That's what we'll be moving into next week, just so you kind of have an idea of where we're going. We're not doing that today. Okay? But in the end, what we do is we simply break down these two angled lines into their vertical and horizontal components. Okay? I can figure out how far north we go during this part and how far south we go during this part, and that'll tell me how far north or south I went in total, this side here. Okay? And similarly, they both go east, so if I add these two sides, this one and this one together, I'll get this green line. And then I'd be able to use Pythagorean Theorem to figure out how long my displacement is. And then a little bit of trigonometry to get theta. Kind of follow there? So what we do is we break all angled vectors down into their x and y components, okay, or horizontal and vertical components, because any angled line is going up and over, down and over, okay, whenever it's going. Okay, so this method we call tail to head method, okay, that's used for any vector quantity, not just displacement. It's also used for velocity, for acceleration, and in unit 2, for force. If I have two forces that aren't pushing in the same direction on one object, the object moves in the direction that is the sum of those two forces. So if I had, let's say, a situation like this, let's say two kids are making a snowman. Okay, so they've got a big ball of snow and they're pushing it. Okay, well, let's say that one of them is pushing it kind of this way, and the other one is pushing it this way. Which way is it going to go? Somewhere in the middle, right? It's not going to go either one of those directions, but if I put them on top of each other, tail to head, okay, that is what the snowman should do, or the big ball should do, as a result of those two forces acting on it. Agreed? All right, so that's kind of what we're going to be looking at. Okay, but for today, we're going to go over colinear vectors, because that's review from Science 10. Okay, we're going to talk about this tail to head thing, that's what I just showed you. Okay, and understand that vector quantities have magnitude and direction, right? And that we all vector quantities are added the same way. That's what I just showed you there. Displacement, velocity, force, we add them all the same way. In fact, it doesn't even matter what the units are during that process of doing all the drawing and calculating. It only matters at the end when you put the final units on. They're all done exactly the same. All right, so when we were talking about like displacement and stuff like that back a few days ago, okay, a vector quantity has obviously magnitude and direction. So that little red line there that's pointing about where the car is going says that the displacement of the car is 2 kilometers, 30 degrees north of east or above the x-axis, okay, whatever their reference is there, okay, but it's 30 degrees from horizontal. Okay, everybody with me there? So it's got magnitude and direction. Okay, when we're drawing vectors, right, and this is kind of our fundamentals of vector addition. When we draw vectors, the length of the line, the length of the arrow, represents the magnitude, or how big. And then we obviously draw the arrow in the direction of the vector we were given. Okay, so if this line here is 2 kilometers long at 30 degrees north of east, then a line that is 4 kilometers long, 10 degrees east of north, would be twice as long and pointing in a different direction. Agreed? Okay, so if I drew that, okay, it would probably look something like this. Right? That would be 4 kilometers, and this would be 10 degrees. Okay? So scale's important, basically, is what you need to get out of this message. Scale in a vector diagram, which is what this is important. If I don't reflect scale, then my diagram might disagree with my math. Okay, so if we go back to what I drew here, okay, I did a decent job, not great, but a decent job of the scale on this diagram. This line was 100 meters, or 100 kilometers long, or 100 meters long. Okay, this one here was 30 meters long. It was about a third as long as this one. Okay, I reflected the scale. I didn't measure it because we don't have that kind of time. Okay, we don't need to measure it and take a ruler out and use a protractor. Don't. Okay, you never need to be that accurate. I just have to take it into account. This was a 20-degree angle, so I made that one smaller because it was only 10. Okay, I try to reflect scale as best I can. The reason for that is if I don't, and I end up making this line too long, when I calculate my answer, I'll look at my answer and then I'll look at my drawing and go, well, I must have done the math wrong. Okay? When in actual fact, what people screw up most often in vector addition is the picture. Okay? But we all have this thing in our mind about math is hard and I'm not good at math, which is crap, by the way. Okay? But that's what we have in our mind. So if we make a mistake, we automatically blame the math Okay, we must have done the math wrong, as opposed to, I couldn't possibly have screwed up a drawing. Drawing's easy. No, it's not. Okay, this is the hard part. Getting the drawing right is what people screw up all the time. They do the math right, they look at their answers, they don't agree, and they blame the math. Okay, blame the drawing. It's usually the drawing. All right, so scale is important, okay? So the length of the arrow is proportional to the magnitude of the vector, okay? And obviously we draw it in the direction that the vector was given. So 30 degrees north of east, 2 kilometers long. This one's 10 degrees east of north. It's 4 kilometers long. Okay, it's pointing a different direction. It's about twice as long as the other one. Okay, really important to reflect scale as best you can when you're drawing vectors. Okay, so if we have to add vectors to one another, we draw the vector diagram like we're telling a story. Okay? First this happened, and then this happened, and then that happened. Okay? And we draw them one after the other, tail to head. Okay? So when I draw the first vector, okay, I put the tail of the second vector on the head of the first. Okay? And I just keep connecting the dots, so to speak, as I go along. Okay? Most questions work that way. There's some kind of chronological order to them, and you just draw them tail to head. The only time you might run into something that's different than that is like the snowman question, where the two things are acting at exactly the same time. I still have to draw them like one happens and then the other happens. Okay? Because if I just draw those two like this, it says that the snowball broke in half and went in two different directions. Okay? And that's not what happened. And it was pushed and then it was pushed, even if they happen at the same time. Okay, so what we draw here, each vector separately, and then we draw this line here, which we call the resultant. Okay? The resultant can represent lots of different things. In this case, the resultant represents the overall displacement of the object. If those were two force vectors, it would represent the net force acting on the object. If they were two velocity vectors, it would represent the average velocity of the object. Okay? So the resultant is just the sum, okay, or the end result of all the vectors that are involved. And it always connects the first point and the last point. Okay? Everybody with me there? This stuff's all pretty like common sense stuff, pretty straightforward. All right, so in this situation here, we've got this car moves 275 meters due east, and then 125 meters due east after that. So this first vector here, okay, is 275 meters due east. This one's 125 meters due east. Okay, they did a good job of representing the scale. One is obviously much shorter than the other, and they both point due east. Okay, so what's the overall displacement? meters east. Right? Okay, so this line here is 400 meters east. Okay, that's vector addition. We draw the vectors tail to head, and we add them together. Now, what if, instead of saying it went east, from east 125 meters, what if we said it went west? Okay, so here's my 275. Okay, where would I draw my 125 now if they turned and went 125 west?
Kind of like in the opposite direction, but like still tail ahead, so you put the bottom of it there and then go towards the left.
Exactly. Okay, draw it like that. Now my overall displacement is
150?
yeah, 150. 150 meters west, or sorry, east, sorry, still east, right? We're still going east here. So our resultant, now instead of being this red line, is actually that one. Okay. Everybody all right with that? Right? Doesn't really change anything. What if that one was south? How would I draw it then? Exactly. I still draw it tail to head. I just make it point whatever direction the vector tells me to point. Now, my resultant looks like this. always the same process. Put a tail to head, and then at the end, draw a resultant line that connects your initial to your final spot. Alright, so that's what we've just done there. Okay, all vector addition is done like that. All vectors are drawn tail to head. Alright, so now this will be new. We've never done a perpendicular vector. So in a perpendicular vector, we still draw them tail to head, still the same car, they went 275 meters east, and then they went 125 meters north. Okay, that means that my resultant, okay, or the change in position of the car is now represented by this red line. Right? So I need to figure out how long that line is, so I have the magnitude of the displacement, and I need to figure out its vector. That is, what direction is it going? So, which angle do I find for the direction? Would I find this angle, so let's say this one's A, this one's B, and that one's 90 degrees. I probably don't need that one. Okay, so which of these two angles, A or B, would I find? But that's what a lot of people do, right? Because they're like, this is where I ended up, so I've got to find the angle that's about where I ended up. Except that when you tell somebody what the displacement is, you tell them how far and in what direction they went, not what direction to get back. Okay? This angle, angle B, tells me how to get back to A, right? I always want to find the angle that says what I did, not what I would have to do to return. Right? So what I always tell people is if you're confused, once you've drawn your resultant, okay, circle your initial point. And wherever that circle goes through the triangle, that's the angle you need to find. Okay? All right. So how will I calculate these two things? I need to calculate that angle, and I need to calculate how big the red line is. All I know is the two blue lines. So let's start with the easy one. How do I calculate how long the red arrow is? Right, I use the Greek geek, okay? Pythagoras studied triangles his whole life, okay? So we call him the Greek geek, okay? We use Pythagorean Theorem. All right, well, Pythagorean Theorem's pretty easy. C equals the square root of A squared plus B squared. So for this one, that's going to be 275 squared plus 125 squared. Square root of 275 squared plus 125 squared. All right, so my overall displacement has a magnitude of 302 meters. All right, so I know this red line here is 302 meters long. All right, how do I find the angle? What's that? It's been so long. Trigonometry. SOHCAHTOA. Here's where SOHCAHTOA comes into play. All right? So just as a quick review, in case you're going, oh, SOHCAHTOA, I've heard that before, but I don't remember what it means and I'm afraid to ask. Okay. The SO part of SOHCAHTOA, sine of theta equals the opposite side over the hypotenuse. Okay, ta. Okay, so I'm sorry, not ta, ka, toa, that's the thing I was thinking of. Okay, so ka, so this is cos of theta equals the adjacent side over the hypotenuse. And toa, which is my favorite one, okay, keep screwing this up, toa equals, okay, tan of theta equals the opposite side over the adjacent side. So I'm trying to find theta. I want to find this theta right here, right? I have all three sides, so at this point, I could pick any of these and they would work. I like to go with the ones I didn't calculate. The question gave me the opposite side and the adjacent side, so just in case I screwed up, just in case, okay? Just in case I screwed up, I want to use the two numbers they gave me. So I'm going to use the opposite side, 125, and the adjacent side, which means I'm going to use tan to figure out what theta is. Right? So in doing that, I have to remember that the tan of theta, which is what I'm looking for, equals opposite over adjacent. I want to get theta by itself, which means I have to take the inverse tan of this side. So theta equals tan to the minus 1 of the opposite side over the adjacent side. Okay? How do I know opposite and adjacent?
Opposite is the one opposite of the angle, so if you draw that one, then the opposite side.
Right. Okay? If you're opposite, okay, you're not touching the angle. If you're adjacent, you're touching the angle. Right? So the 275 is adjacent or beside or touching the angle. The 125 is opposite because it's over and away. Okay. All right, so that means then that I'm going to punch into my calculator tan to the minus 1 of 125 over 275. All right, that's going to give me my angle. It's not going to give me my direction. It's going to give me my angle, which is part of the direction. So when I punch that in, I hit second function, tan, so that gives me tan to the minus 1. 125 divided by 275. Oh, I'm in radian mode. That's how you can tell, by the way. Okay, you get a decimal, you can always check that. So I got to go to mode. Make sure, guys, you are in degree mode. Your calculator, if it has been reset, defaults to radian. Don't ask me why. Okay, but it does. You need it in degree. All right, let's try that again. Second tan of 125 divided by 275. Now we'll get a good answer. 24.4 degrees. Okay, I have three significant figures, so that's what I'm going to keep, 24.4. All right, so that's my angle. It's 24.4 degrees, which direction? Okay, this direction, so this 24.4 goes right here. This angle here is 24.4 degrees, and it is north of east. Okay, notice that I say north of east and not northeast. Okay, northeast is an entire sector of the compass. There are two 24.4 degrees northeasts. One is east of north, that's not the one we have. And one is north of east. They're two different directions. Okay? There's really only truly one angle that is northeast, and that would be 45. Okay, because it would split it right down the middle. Right? So this is north of east, and here's how I determine that. Right? And I do this in my head. I used to actually physically do it. It's okay if we do. Okay? I point whichever direction the angle line is touching. Okay, so my angle arc here is touching due east. Okay, whatever direction I have to open my hand to make that shape, okay, that's my first direction. I go north of east. Okay, if it was east of north, I'd have my hands pointing north, open up to make the shape. I'm going east of north. So our final answer here, our total displacement for that is 302 meters north of east. Sorry, 22.4 degrees at 22.4 degrees north of east. Okay, that would be my final answer. Questions on how that one worked?
You wrote down 22.4 degrees.
It's 24.4 degrees. I have not had all of my coffee yet. That's my story, and I'm sticking to it. I'm not senile. What was I talking about? All right, so this is what we just did, okay? All of that work, okay? So we've already shown all of that. Okay. All right, I want you guys to try this one. It's all collinear, really, really easy. You can, okay? So draw the vector diagram and give me the final displacement. All right, so this race obviously occurs in the most boring town in the entire world. Okay, so we have people who move forward 10 meters. Okay, and then they move 5 meters. Then they move 25 meters. I maybe didn't do scale very well here, but we'll do our best. Since it's collinear, scale's not really that important. Okay, on a collinear one. All right, so what's the total displacement? 40 meters forward. Yeah. Okay. So that one's pretty straightforward. Literally straightforward. All right. Okay. This one I want you to try and get the diagram drawn for it, tail to head. There's 3 vectors. Okay? 3 vectors, but it ends up only being a perpendicular result. Okay? So I want you to draw the diagram and see if you can figure out how to get the total displacement. Okay? I'll give you a few minutes and then we'll walk through the rest of it together. Okay, so I'm going to kind of walk through the diagram here first, and then kind of, if you are stuck, then you can kind of give it a second try here. So the first thing is that they go 0.8 kilometers south. So I'm just going to kind of arbitrarily make my starting point right here, and I'm going to go 0.8 kilometers south. Okay. Then it says they go 1.2 kilometers east. So I'm drawing them tail to head. The last thing they do is go 0.3 kilometers north. Right? So that's roughly to scale. It's not exact, but it's close enough for our purposes. So where do I draw a line? This would obviously represent their whole trip, and I could calculate the distance from it, but where would I draw a line that represents their total displacement?
From the tail of the green line.
Exactly, from my initial point to my final point. Okay, like so. So this line has both a magnitude, a length, and a direction, a vector. All right, so this will represent my total displacement's magnitude. This will represent my total displacement's vector. Now, if I want to find that line, how do I do that? I mean, I drew a triangle there, but I don't know the sides of it. Or do I? Yes, you could. No.
I'd say that we are, since we already know this side length on the left, we just see what 0.3 what x equals 0.8 instead of 0.5.
Yeah, exactly. That's the very mathematical way to say it, okay, is to go, well, we know that they went this far, they went 0.8 here, and that this one's 0.3, and if we put those together, we get 0.5. Absolutely, that's the mathematical way, okay? And that's what we would have to do in our calculator. From a more, like, I'm trying to reason it out and see it visually, she went 0.8 kilometers south, and then back, I mean, still, it was over here, but she came back in a north-south direction, 0.3 kilometers, which means she only ended up, from a north-south perspective, half a kilometer south of where she started. Everybody with me on that? Okay, so what I did there is I said, this red triangle has a y component, a vertical component or a north-south component, okay, and an x component, an east-west or horizontal component. I can calculate this y by simply going 0.8 kilometers south plus 0.3 kilometers north, which gives me 0.5 kilometers south. And then this side has got to be equal to this side. Everybody with me there? Okay. All right, so we got that this side here must be 1.2 kilometers. Everybody good with that? All right, so I'm going to let you guys go from there and see how you do with the rest of this. We want to calculate d and theta. All right? That's fine. Yeah, you're just going to get east of south, and I'm going to get south of east. Well, I'm going to go this way. Yeah. East of south, yeah. Yes, the complementary angles would be right. So there would be one answer that would be east of south and one that would be south of east, but they would both be right. Like that. Okay. Recording. Okay, so let's look at the final steps for this one here, guys. So if I want to calculate the magnitude, that is how long d is, then I'm going to use Pythagorean Theorem. All right, so for Pythagorean Theorem, the magnitude of d will be the square root of 0.5 squared plus 1.2 squared. So square root of 0.5 squared plus 1.2 squared. All right, so that line there is 1.3 kilometers in length. So her displacement is 1.3 kilometers, the magnitude anyway. Right, now I've got to calculate the direction. This is the direction I want to calculate here. Now, I did have someone ask, what if I drew my triangle this way? Am I going to get it wrong? And the answer is no. The dimensions of that triangle are identical to the one that I drew. What you're going to get that's different, but still correct, is you're going to get the complementary angle to the one that I calculate, and both will be right, because they are, after all, talking about the same direction. When I calculate mine, I'm going to get x many degrees south of east. If you drew the triangle the other way, you'll get x many degrees east of south. But they'll still be talking about the same direction, so both are correct. Okay? So when I calculate theta here, theta is going to equal tan to the minus 1, because I'm going to pick the opposite side and the adjacent side. Okay, so 0.5 over 1.2. So second tan of 0.5 divided by 1.2. And we're looking at 22 point, actually we only got 2 sig digs here, so 23 degrees. Okay, and for me, because I drew this angle here, that is going to be south of east. So I get 23 degrees south of east. So the two possible correct answers for this would be the displacement of the object is 1.3 kilometers at 23 degrees south of east, or at 67 degrees east of south. Okay. No, I know you're not doing the robot. What are you, is there something I'm missing? Okay, because that is tricky. That's why I ask. I'm not trying to make fun of you. Okay, just a lot of people struggle with the direction part of it. Okay, so the other way, guys, that you can do this, if you're trying to figure out is it east of south or south of east, okay, when you draw this angle arc, okay, put your pencil on whatever direction it's touching. Okay, that's east. So it's going to be of east, and then whatever way you go from there, south of east. Okay. All right with that. Sometimes it's good to just, every time you do one of these questions, draw a compass, okay? Put that direction in there. All right, it's here, that is south of east. And whatever works for you. There's lots of different ways for you to sort out those directions, okay? If you're like a bodily kinesthetic learner, doing the hand thing is probably going to work better, okay? If you're, more of a visual person, then a compass might work better, okay? If you're auditory, then what I did here, talking myself through it, I'm starting out east and then I'm going south of that. Okay, whichever way works for you, okay, that's the way you should do it. All right, because I often see people on the final exam and they're trying to hide it, but they're like, and they're trying to, do the hand things. There's nothing to be shy about. Whatever way's going to work for you to figure it out, you do it. Okay. All right, questions on how that one worked? Okay, so that's kind of headed towards where we're going to go. Those were all still perpendicular. Okay, there was nothing that was weirdly angled, right? But that is where we're headed, is to the ones that are all angled, right? So what we did here is the basis for those angled vectors. Okay, what we did was we found the vector components of our resultant. We found its x, or horizontal component, and we found its y, or vertical component. And then we used that to put together our overall result. Okay? So that's why what we start on Monday is going to be called vector component addition. We resolve every vector into its x and y, and then we can add the x's and add the y's together to get a full picture of what we're doing, which is what I showed you right here. Okay, so this is where we're going to be headed. Okay, what we did is we found, there, what we would do is we would find black y and black x. We would find red x and red y, and we would use them to find green x and green y. Okay, this is where the trig is really going to come into play. Right? If I want to find this side, I'd have to multiply 100 by the cos of 20 because it's the adjacent side. If I wanted to find this side, it's the opposite side, so I'd multiply 100 by the sine of 20 to get that side. I'd resolve it down into its components. Okay? We have to break every angled vector up into how far over and how far up or how far down does it go. Okay? That's what we're going to head to next week. And at first, it's going to be really slow. Right? It's going to take like 25 minutes to do one question. And that's fine. At the start, you're slow. But once you realize that it's always the same steps, you get faster and faster at the steps, and pretty soon you'll be doing a question like this that originally took you 25 minutes in about 6 or 7. Okay? I'm not going to lie to you. You're not going to do one of these in 30 seconds. Okay? It's going to take you a few minutes because there's lots of steps. There's lots of individual things to type into the calculator. Right? But you'll get faster and faster at it. Okay, stuff about your acceleration lab, okay, before we go. For your acceleration labs, okay, remember that they're due, what do they make it, Thursday, right? Okay, Thursday of next week, so you can pop in and see me, okay, Monday at lunch, Tuesday at lunch, Wednesday at lunch, okay, any of those days after school, okay, I'm here for a little bit after school, okay, I'm here in the mornings if you're desperate, but I'm usually getting stuff set up and I'm a little like flustered usually in the morning, which you can pop in, okay, if you're needing some help, guys. But what I won't do is, you know, if you're emailing me at 9 o'clock at night, Mr. Could I got a question about my lab, okay? You've got lots of opportunity to come and ask me in person, and it's way easier to give you feedback on your lab in person than it is for me to call it up on my phone, because I don't take my computer home, okay? And then try and put in comments and send stuff back to you that you might not understand, okay? I really prefer to do that process in person, so if you're wanting help with that, pop in and see. Okay? All right, we'll call it a day there.